Okay, thank you all for attending and welcome to the November Statmos online seminar. Remember, Statmos is the research network for statistical methods for atmospheric and oceanic sciences, and you'll find more details at statmos.uw.edu. And remember, the basic idea is to get people networking and talking about atmospheric sciences and oceanic sciences and statistics. So think about applying for travel and so on and so forth. Okay, so today we're very lucky to have Douglas Nychka, or Doug Nychka, as probably most of us know, from the National Center for Atmospheric Research. He's the director of IMAGE, which is the Institute for Mathematics Applied to Geosciences, and is also a senior scientist in the GSP, Geophysical Statistics Project. And everyone knows how influential he is in terms of all these areas, so statistical methods for basically atmospheric and oceanic sciences, and the development of a lot of spatial models and spatiotemporal models. And so today he's going to talk about statistical models for large spatial data sets, and thanks again, Doug.
All right. Thanks a lot. How is the sound here, Peter? Is that?
It sounds great. Perfect.
Okay, great. So I'd like to welcome everybody. I'm sorry you're not here with me. You might be sorry though. I'm just going to turn this briefly, and you can maybe get a view of outside. It's just a Siberian landscape out there. I think the herd they heard the ski places weren't getting snow, but they missed. We're getting lots of snow in Boulder, and it's pretty cold. But anyway, so this is in contrast to my first overhead here, the title where it's still green and fall. Okay, so over the past years, I've become interested in trying to extend spatial methods to large data sets. The bread is going to be a description of an application, and I'm going to take something from NARCAP. It's a fairly involved application, and I apologize if in the end it goes a little bit too quickly and it's not quite clear what I'm doing. But really the main point is I just wanted to get that out there and remind people that NARCAP is still an important data set to work with, and it's a nice litmus test to see how different spatial methods work. The statistical method we're calling lattice-Krieg. It seems like if you have a spatial method that somehow doesn't have the phrase Krieg in it, it's not quite right. So we added that in. It'd be great to create a spatial method that's called like Krieging or something like that, just to really emphasize what you're doing. But anyway, so here's the cast of characters here. Lots of people. Many of these are Statmos people. Some of them are a little bit outside our network. And really, all of these people in some shape or form have contributed to this talk. All right. So here's the bread of the sandwich. It's a statistical application. What I'm showing you here is an aerial view of part of Boulder. It was taken from the NCAR research aircraft as it was taking off. Now, let me see here. Peter, how do I do the pointing again?
So if you click on the arrow and then just point to where you want to be.
Is the NCAR Mesa Lab where I'm sitting right now. So what you see here is South Boulder in the foreground, the foothills of the Rocky Mountains behind NCAR, and then finally up a little further, that's the Continental Divide, and of course that's a high alpine environment. I like this picture because it really emphasizes this problem of resolution in global models. So what you're seeing here is if you had a global model that even did have a decent resolution, it would basically collapse all this to a single spatial point. And what I mean by that is interpreted as an average over this entire grid box. Obviously, if we want to study climate change for South Boulder, it doesn't help to consider this broad average that also includes the effects of sort of high altitude and alpine alpine meteorology. Okay, so we want to run global climate models because they build in all of the large-scale interactions between the ocean and the sea ice and land effects and the atmosphere. But on the other hand, we want finer resolution to do climate impacts and detail. Take a global model and we run that over the Earth. We take a particular study region. For example, I'm showing you here the NARCAP domain for North America. And just within that domain, we run a high resolution model. Sometimes that high resolution model takes information from the global model everywhere. Sometimes it just takes it at the boundaries. And so you can see that in this particular case, I think this model where we have some moisture at the boundary of the produced by the global model on the west coast of this domain, and you can see that it's as it moves into the domain, the regional model has actually created a fine, detailed kind of precipitation field based on that. So I probably don't need to remind the there really doesn't exist something that's called a climate model. There are deterministic numerical codes that are highly detailed and they simulate weather. And what makes them a climate model is that you can run them for very long periods of time and they remain stable. They remain physically realistic. So the way you actually take a model and determine what its climate is actually very similar to what we do with ordinary observations. We would take a global model and we would run it for 30 years. We would we would store all the weather that it's producing, say on a daily basis over those. The same deal with this coupled scenario where we have a global model and then forcing a regional model. We would run the global model for 20 years, say, or 30 years. It would produce these boundary conditions, which would then be downscaled by the regional model. The regional model would produce much more detailed weather over this particular region. And we would treat that as weather observations and take the averages, and that's how we estimate the climate. The reason I'm belaboring this is to make an important point, is that even though these are deterministic models, and this is very much a physical modeling enterprise, at the very heart of this, to interpret them, you need to use statistics. So I would say it's a very persuasive reason why Statmos needs to exist and needs to persist, in that we're always going to be having to do statistical analysis of these simulations. So I'm not, perhaps some of you have heard the NARCAP story before. So Steve Sane and I were working on the original design of this. The original design involved 4 global models, forcing 6 regional models. Remember that a single pairing here is a particular global model and a particular regional model. So in this original plan, we had 24 different choices. We had 4 times 6. The grant got good reviews. It was a multi-agency effort. Lot of support, but they said, but you have to cut your budget. You have half your budget. So the decision was to run a half fractional factorial design. The plan is for NARCAP is to do 12 pairings of these global and regional models. If there ever is more money, the full 24 can be completed. But these 12 are a balanced design, and so they allow a statistical analysis in ways that wouldn't be possible if this was just sort of a happenstance choice of 12 out of the 24. To my knowledge, this is one of the few cases where a deliberate factorial design has been done on such a large computational effort. I'm going to talk about these red boxes here. So within this, we have a full 2x2 factorial of 2 global models, these 2 guys here, and 2 regional models. This is a U.S. Canadian effort. So CCSM is the NCAR model. CGCM3 is the Canadian global model, and so and then we have the Canadian regional model, and also the sort of an NCAR based regional model. So I'm going to talk about those particular model runs at the end. So keep in mind that this involves 4 pairings. I'm going to show a lot of groups of 4 at the end, and the groups of 4 represent these 4 different choices of the models. Okay, so let me just center that and go to the next page. Okay, so just to end this data motivation, we have a simple question. How will the seasonal cycle for temperature change in the future? Based on the NARCAP experiments, we can run these models under present climate and under a projected future climate, and we can just ask the question, will there be a difference? And if so, how? So that's what we'll be talking about. Because these are only simulations that have been done over 20 or 30 years, we know that there's some inherent variability in these, just like we wouldn't expect a 30-year climatology to be completely representative of, say, like a 100-year set of weather. So we have to do some statistics on it. We have to do spatial statistics, and we have a large spatial data set to deal with. The NARCAP grid, let me just see if I can backspace this quickly. The NARCAP grid is about 9,000 points. So nominally, to do spatial statistics on this, we have 9,000 locations to build our models. Okay, so let me tell you a little bit about Lattice Krieg. since many of you are expert in spatial statistics and know more about this than I do, I'm not going to belabor a lot of the details. They're in a recently produced tech report of ours, and this paper is also in press for Journal of Computational and Graphical Statistics. So if you want all the details, you can read them. But let me just give you a heuristic of this, and I'm doing this for a little bit of a devious reason. This is a route to building a spatial model which may seem really different than writing down a covariance, and that's sort of what I wanted to emphasize. That's basically the hook that allows us to compute for large data sets. At the end of the day, we will have a covariance function and we will have a spatial model, but we're going to get to it via a very different route. That different route is going to generate different kinds of matrices that have lots of zeros in them. And so let's get started. Here's a single bump. You've probably been looking at this for about 30 seconds, and you'd say, "Yeah, you've shown me this single bump. Let's get going here." Okay, so what we can do is we can add another bump to that and consider the superposition of both of these. So I'm adding these two bumps together. Notice they have equal weight, and notice that when we add them together, we actually produce another bump, which is neither at the maximum of either of these two. So we can build a little different shape just using bumps and weights. We can take half the weight of the second bump, and notice that produces something that's a little bit skewed here. We can also, if we think of these as sort of dumping sand piles, we can also say, let's take some sand away. And so a negative weight here, or a negative coefficient, if you will, gives us a shape of a curve that goes up and then down. So again, we're sort of able to build shapes of curves that are very different than the parent bumps that are figuring into this. Okay, so what I'm doing is I took 8 of these bumps, and let me emphasize that these bumps are all located at equally spaced points. That's going to turn out to be very important for this. They have random weights. That's also an important ingredient. And notice that when we do all this, they conspire together to give us a nice random curve. Okay, so we're out in the west here. We got lots of open space. We think big. It's not just Texas that has a handle on that. So if we use 8, why not go to 16? So here we go. We're adding now smaller bumps. So I've taken these bumps and shrunk them by a factor of 2, and I have twice as many. I have 16 now, and so notice that when we add random weights to these, we get another nice sort of pleasing random curve for these. Notice that the structure of this curve, the wiggles are at sort of half the scale of the other. And that's going to be an important ingredient now. If you're paying attention, and if you just got that, so I'll repeat it, notice that the structure here is at half the scale of the previous example. That's all there is to multiscale, or at least in my limited understanding of multiscale, that's sort of how things get off the ground. We're basically building models that do the different components represent different scales of a curve. We can add these together now, and so now what we have is we have a random curve that is the sum of these of the curve that's built from the 8 basis functions and the curve that's built from the 16. So I've put in those little 16 dots there. And I've added these together. So that's it. That's how I'm building my random functions. So notice that this description, what's interesting, at least initially, is that I'm telling a story directly about my random curve. I'm not writing down a covariance. Now, of course, if I add a stochastic model to these coefficients, then of course we could write down a covariance, and it would be implied by the kind of structure that we're building into this, and we're going to get there in a moment. But I just wanted to point that out, that we're starting at a little bit more basic level here. Okay, we're interested in spatial statistics, at least I am. I'm assuming most of you are too, and so we have to go at least to 2 dimensions. Conceptually, I'm not going to try to draw any animations or pictures of this, but what you want to think about is that now our sand piles really do look like sand piles. Instead of just being located at different points along a line, we actually have a regular rectangular array of points here. And it looks like I have 8 points in this. So there's actually 64 different basis functions or different bumps that we're going to be working with here. The beauty of the lattice-Krieg approach is that it's computationally efficient. And so it means we can be very liberal with the number of basis functions that we're throwing down. And you can imagine the basis functions are going to grow very quickly here. If we start with a lattice of 8 by 8, that's 64 basis functions, you say, well, that's not too bad. But then we go up to the next resolution, and that would be 128 by 100. I'm sorry, we go up to 16, and so that would be 256 basis functions. We go to 32, we're adding another 1,000. We go to 64, and we're adding another 4,000 about. So these things grow pretty quickly as we're adding levels. Just to emphasize that, and to bring in a little bit of a detail here that I'm going to I'd like to dwell on in a moment. Here is North America, a particular projection of it. And what I've shown is a blow up of New England, and given you sort of my scheme for a lattice for this. This is a 2-level lattice. The blue crosses here are the first level. The black are the second level of lattice, and the red points are the third level. And so notice that as advertised, these are always decreasing by a factor of 2. And notice that what's a little bit different about this is I'm adding a few boundary lattice points here. So even though my data might stop here at the sort of this part of northern Quebec, or I don't know, maybe I think that's Quebec. You know, I'm actually adding a few more boundary points here. That's to diminish edge effects, and I'll show you how nicely that works in a moment. I wanted, maybe this is a good point to make. This is a good time to make a point about lattices. So what's really strange about the lattice-Krieg model is that sometimes I'm thinking about the lattice points as actually being spatial locations, because they actually tell me where to center the bumps for my basis functions. But in other ways, we're really just thinking of the lattice as a way to tell us how things are connected. So for example, this lattice point is connected to its neighbors like that. And those connections are defined statistically. And when we define those connections, really, we don't have to worry too much about the geometry. And so what I'm sort of alluding to here is that there's an aspect of the lattice which is really not geometrically dependent, or is much more flexible. So we could actually have a lattice on a surface and define connections that way. We could have a lattice on the sphere. That would be another way to generalize this. When people talk about social networks, they talk about nodes and connections between nodes, and obviously there's not a sense of space there. That's sort of what I'm alluding to. Okay, so like most statistical talks, at some point we're going to have to write down some equations so I can tell you exactly what I'm doing. And so here's a way to get started on that. We have spatial data. In this case, it's going to be the temperature fields for North America that are simulated by the NARCAP regional climate model runs. Or in this particular example, these are actually going to be coefficients associated with principal components when we expand the seasonal cycle in 4 principal components. So this is going to be some kind of observation. In our case, it'll actually be a derived one. Regardless of what we observe, we're thinking that it's the sum of a smooth surface G. That's our spatial surface we want to estimate. We observe it at particular locations. And of course, the whole point here is that we would like to then generalize that spatial surface to arbitrary locations. Here's how we're doing it. I should also say that as part of this model, there's a measurement error component, E sub I. So really, spatial statistics is this fundamental problem where we have a spatial signal plus spatial noise, and we're trying to affect a separation of that. Here's the deal. So we're representing G as a sum of basis functions, and I've told you a lot about these basis functions. When you hear basis functions, what you want to think about is lots of bumps arranged on lattices of different resolutions. They're all fixed. We prescribe what they are. And really what's going to interact with the data strongly is to figure out what the heck these coefficients are. So to put it very simply, we basically have observations, and we'd like to find out what are the most likely values of these coefficients given the data. So we can phrase it that way as sort of like a conditional distribution. All right. What I've done here is I've taken that observational equation and I've collected it as a vector is equal to basis function matrix times the coefficients, and then we have the error floating along there. This X matrix could actually be pretty big. And just to make it concrete here, we're working with the NARCAP data, 9,000 locations. So X has 9,000 rows. I showed you sort of a typical kind of lattice we might throw at this, 4,000 basis functions. So X would be 9,000 by 4,000, and we would have 4,000 coefficients here. So that's our kind of model. It sounds a little bit megalomaniac, but we have lots of sparsity here, and that's going to come and save us and make it computable. There's another layer to this model, and I'm sure you've all been waiting for this. The spatial people is we have to tell a story about what the heck C is. And so what we're going to assume here is C is going to follow a multivariate normal distribution, mean 0 just to make this a simple talk, and then it's going to have a covariance matrix. It's going to have a leading coefficient, rho, and then it's going to be represented as the covariance matrix is going to represent it as an inverse. And so this Q is going to appear throughout the rest of this talk, and that's really a fundamental quantity here. Q is the precision matrix. It's the inverse of the covariance matrix. In a moment, I'm going to tell you exactly how we're going to model Q. But that's really the elements of this. what I've casted out here, so this may cause a lot of consternation for some of you, but let me just say that I have this top level model, which is telling us about the observations. I have this next level, which is a statistical model for the coefficients. And I'm going to refer to this as a hierarchical model. It's not Bayesian because I haven't put any priors on this yet. And I would just like to throw out the contentious remark that Bayesians do not have a lock on hierarchical models. It's okay for other kinds of people to think about hierarchies of statistical models without becoming Bayesian right away. Although I think most Bayesians would say it's going to about and not really dealing with the conventional way that geostatistics is done. I want to pitch this as a thinking about a cost function approach or a variational approach. This is how splines are presented. So the way someone thinking about splines would formulate this problem is I need to come up with a cost function where it represents the fit of my model. In this case, my model is this this sum of basis functions times coefficients, the fit of my model to my data, and then I also want to penalize that surface I'm trying to estimate in terms of roughness. When we do this, and I'm going to show you the formulas in a moment, we really end up with a ridge regression kind of formulation. And just to keep people sort of thinking about this, I've actually jumped ahead and written the ridge regression formula down there. So no surprises here that X is our regression matrix, X transpose X, and then we have the measurement error, we have the leading coefficient that's in front of our covariance matrix. We have our Q, which is the inverse of the covariance matrix. We take the inverse of this whole thing, and then of these coefficients if we condition on all the other parameters in a Bayesian model. So it's a very standard way. It would also be what we would be led to if we simply want to do Kriging with the with this weird model that I'm spinning out. Let me also use this formula to explain to you sort of the magic of how to do fast computing. So the way to do fast computing with spatial statistics is to generate sparse matrices. And that's just a fancy way of saying we're going to generate matrices that are big, but they have lots of zeros, and we know where those zeros are. And we're going to exploit the fact that when we do computations, we don't have to do any computation on a zero because we know what 0 times a number is going to give us. X is sparse because it's essentially bumps where there's 0 beyond a certain range. X transpose X will also be a sparse matrix. I'm now going to tell you about a model for Q, and Q is also going to be a sparse matrix. Now, the interesting thing about this, and it took me a long time to realize this, what I mean by long is I've been in this business a long time. Long typically means at least 10 years, maybe 20. You can have a covariance matrix that is completely full. It has correlations among everything, and you can take its inverse and actually have an inverse which is quite sparse. And so that's the magic of sort of matrix inverses, and I'll be showing you that in a moment how that works. Okay, but before we get on to Q, let me just tell you a little bit more about these computations. So what I've done is I've gone back to this spline motivation of fit of surface to data, roughness of the surface. I'm now going to add on some more penalties for other parameters because, as you know, most self-respecting spatial models are going to have different additional parameters. for quite a bit of this, and I'm really just leaving out this extra stuff. Might be a prior that we would put on these parameters theta that are controlling this Q matrix. So in spline terminology, we would call Q a roughness penalty, or this whole term is a penalty matrix. But really for us, it's really just a spatial model for these coefficients that live on a lattice. Okay. The reason we want to go through this is that we can also get estimates of uncertainty, that besides minimizing this cost function, we can actually interpret this as a log posterior. And so sampling from this posterior is going to give us a distribution of parameters and coefficients that control the uncertainty of it. And so that's a comment for the data miners out there, that there's more than just finding estimates, that we can actually use these structures to get uncertainty. A few of their properties. The Q matrix is a precision matrix, and so we're going to sort of describe what Q is in a backwards kind of fashion. Here are our coefficients sitting on the lattice. So in this case, we're actually taking the lattice literally as spatial locations. This center value, we're going to say the distribution of this center value is found in the following way. We take the nearest neighbors and we apply weights to all the nearest neighbors. So we basically take the weighted center point, ask me what's the distribution of C, what I say is you apply this filter and you get white noise. And you'd say, well, that sounds a little bit backwards. Why don't you just tell me what the distribution of C is? It turns out that this way of describing it is in the precision space. If I reverse this and actually told you how to get C directly, we'd be thinking about the covariance model instead. And let's see here. Peter, is it possible that I can write something on the board here behind me?
I don't know how clear it is. That's the problem.
Okay.
There's a little fuzziness. Yeah.
Okay. I can write it pretty big. Let me
Go for it.
Let me try that. Okay.
Someone says right big as well. There was a question along the way asking you what the basis functions were as well.
Okay. The basis functions are polynomial defined bumps. In the two-dimensional case, they're they're a little bit exotic that way. Okay, so I'm gonna write really big. I guess this is gonna seem a bit like Sesame Street, but maybe that'll help you read this. So I want to walk you through where the precision matrix comes from. So if I take those weights that I just described for one particular case, this is going to be a with is normal 0, 1s. Okay, so there's a matrix B. Now, if you think about the matrix B, it has rows where it has alpha on the diagonal, and then it has 4 minus 1s on a particular row. The rest are 0. If you check out what the covariance, what the implied covariance is here, well, it's going to turn out to be B inverse transpose times B inverse. And so if we now say, well, this is equal to the inverse of Q. Here, we end up with Q is equal to B transpose B. And I'm looking, how did that work?
It's not bad. It's a little pixelated.
But I think now if you just look behind me, you can see that. So so just to recap here, B is a sparse matrix. The precision matrix is going to be also sparse because it's B transpose B. Q inverse need not be sparse, and the autoregression. And we know that you can have an AR1 process where the precision matrix for the AR1 time series is very sparse. But if you actually look at the implied covariance, well, the correlations fall off exponentially. And so we actually have a dense matrix there. Okay, so very, very briefly, here's this noise. And so notice here that when I set alpha close to 1, I can actually get quite a bit of spatial dependence among the coefficients, even though we're just applying local averaging to generate these. Okay, and then this is just to remind you that this is more than just a model on the lattice. So I'm taking my coefficients again. A 16 by 16 lattice. I'm just guessing here. So I have about 256 basis functions. I'm expanding those, and I'm using these Wendland bumps that have overlap between the different lattice points. And notice that I get sort of a nice, pleasing as just one a point that's sort of deeper in this hierarchy here of my overall model. Okay, I put this in just to remind me to say this, and this is sort of an important point, and this really makes this spatial model useful. Pretty constrained in the kinds of covariances we can build. But what I actually do is I say, well, it's sort of that Texas mentality is if we can do one, why not do a whole lot more? So we basically take the model for one level and we add it to a stochastic process at another level, and then finally at the third level, which when we're down many kinds of covariance functions. And let me just give you an example of that. So I'm going to make a big leap here. And let me just briefly explain what that is. I'm assuming there, and I'm going to assume that you can just take this whole model and compute the implied covariance of that process. When we do that for one level, I think I'm starting at an 8x8 case here. Here is the implied correlation function for that process. So it falls off in terms of distance. It has a certain shape. This shape is probably pretty close to a Matern family, but there it is. At the second level, similar kind of shape. There's my process. But suppose that what I want to do is fit an exponential. So this dashed line might be a processes, just weighting them by positive weights. If you pick the weights correctly, something magic happens. So here's that first covariance model. Now the 2 means I've added the first and second multi-resolution layers together, weighting by a very particular sort of set of weights. They're basically falling off exponentially by right on top of it. So what I've done here is I've shown you how the multi-resolution is your friend. We're essentially taking mixtures of covariances, and by cleverly, well, I won't say cleverly because I did this, by weighting these in an appropriate way, we can often build many other shapes. Not just the Matern family, but this is quite fast. If we just do a head-to-head comparison between, say, 20,000 observations using the standard Kriging calculations, it takes about 20 minutes. A comparable timing in that case would be about 10 seconds. And so literally, if we're fitting this kind of exponential model to 20,000 observations, the Kriging would take and doable there. Okay, I notice I only have about 10 minutes here, and I always hope to get to this last section, and I think it really is another thing that makes this work. So I would encourage you to sort of take a look at the paper and just take a look at these overheads if you're interested in variance. So it turns out that works. I think it works very nicely. Okay, so we're at the bottom bread of our sandwich. How will the seasonal cycle for temperature change in the I have a present and future, and for each of those present and futures, I've gone to each grid box, estimated the seasonal cycle, estimated the difference in the seasonal cycle between future and present, and here are the principal components of those differences. And so you want to think of these as 4 Tinker toys that I would add together based on tell us how to reconstruct the seasonal cycle to approximate that. Now you might ask, well, why am I only looking at 4 Tinker toys when there's 365 days in the year? Well, the problem is that then the dimensions become overwhelming, because then it means that for every grid point in the NARTAP domain, I would have 365 days to deal with. I would rather it's essentially a level shift. There's our warming signal. So if the difference in seasonality is simply a level shift, actually a warming between present and future, it would emphasize this first principal component. The second Okay, so here's the results for Boulder, just to skip ahead. The black is the raw seasonal cycle that we extract for the Boulder grid box. The dashed is the projection onto the four principal components. So we see the dashed is a pretty good representation. The green is the result of taking these components, smoothing them across space. So doing the 9,000 locations, doing a spatial smoothing of that, essentially trying to separate the spatial signal of this coefficient field from the Notice after all this talk, it's actually very similar to the raw, which says that we're probably estimating these pretty well just from the sample statistics. Okay, last overhead. So one thing we can do is, so let me just describe how I used what 1,000 basis functions. I'm doing a spatial smoothing on 16 different fields. So for each model, I'm smoothing the 4 coefficient fields, and then of course I have 4 different pairings of models here. This first plot is asking the question, is this just a level shift? Is really the difference in seasonality from present to future strong dependence between whether you use the Canadian regional model or the NCAR regional model? Okay, let me skip to the specific Boulder results. So now we're asking the question, so what's the story in terms of change in seasonality for Boulder? These noodle plots are showing you the uncertainty based on the spatial analysis for each of these 4 models. And what we see right away is nevertheless, all of these have a level shift in the warming. All of these show an increase in the summertime, but notice that there still is quite a bit of a range between these. And that is a hallmark of looking at regional studies and regional models, that there's still a lot of uncertainty into how climate change will actually trickle down from the global levels. Some final thoughts on next steps. There's a determinant in the calculus is really the main bottleneck, even when you're doing sparse matrix methods. And there may be ways of getting around that determinant. Mike Stein has a very nice recent paper where he's talking about looking at the score function, the derivative of the likelihood rather than the likelihood itself, and you finesse calculating the determinant that way. Another possibility is to just consider parameter estimation using cross-validation, which when you combine that with an interest in trying to estimate the smoothness of the also enjoy the sort of the kinds of tricks that Michael Stein is exploiting in his paper for the score function. Okay, so just to wrap up here, computational efficiency is gained by compact basis functions and a sparse precision matrix. The multi-resolution can approximate standard covariance families, not just the Matern, but many others. And I should say that probably the thing I'm most proud of here is we actually have a little bit of a lemma that shows this. And it's so unusual to have a nice sort of clean theoretical result in spatial statistics, at this level, that it was sort of fun to be able to do that. And then finally, it's easy to generate uncertainty measures based on conditional simulation. There's an R package out there. There's a new version that I'm about to release, which will allow you to do different geometries besides just the 2D plane. All right. So I want let me just also use this an opportunity to thank the people who made Statmos possible. I think it's been a great success in terms of getting people to talk to each other.
Okay, great. Thank you so much. Right, so we're going to do questions. Everyone does have a chance to open up their mics. It can be a little complicated. You have to push the mic button, which is at the top, and then allow yourself to have permission to here in Chicago. Okay, question. Doug, have you compared your model to Matern
that
in the
is,
spectral domain?
So good question. That is exactly what our theory is attempting to do. So what we show is that, to be specific, in the spectral domain, you're really concerned about the tail behavior, because the tail behavior is how the covariance behaves near zero in the spatial domain. What we show is that you can capture the same tail behavior for a Matern. Intriguing about that is it turns out to be not particularly sensitive to what basis functions you're using, or the particular Markov random field that you're picking either. There's sort of a robustness there.
Right. Matthias asks, for which covariance functions do you know exactly how the basis functions in the precision matrix should be chosen to get a good approximation?
Let's see. So I'm going to focus, Matthias, on that word exactly. I don't know how to approximate anything exactly with lattice Krieg. There is a but exactly what it is, basically you just get what you get. But as I said, there are these weighting schemes that, at least in an approximate way, allow you to choose a lattice Krieg model that's like a particular Matern. Okay.
Okay, thank you. NC State asks, do you need a stationary field, or can you produce a non-parametric, non-stationary covariance constrained simply by the locus movement?
So that sounds like someone who's hung around Monsi a bit. Let me go back to this little build-in non-stationarity. So I'm pointing to that alpha. Why not let alpha vary over space? So we're actually in a case where this lattice makes sense in terms of spatial locations. And we could imagine this lattice slowly varying, where it takes on, say, for example, a value close to 1 here, which would give it a large correlation range, and then maybe over here the alpha is and writing it in terms of a process is that we will always get a covariance function. We're defining a stochastic process, it has a covariance, and we can work that out. Issues of whether or not we have positive definiteness, they're really non-issues, because every stochastic process Let me explain another way to do it, which sort of comes out of the multi-resolution idea. So think about these processes as having so the way we're adding up G is we're taking a weight times a standardized process plus a weight times another standardized process. If we let those weights vary over space, again, since we're defining this in terms of the processes, we will always get a valid covariance from that. Okay, so let me stop there. Maybe there's a
There's one
Yawen
more
Yawen
question from
Guan.
someone else. Excuse the pronunciation. Yeah, it says, please comment on the multi-resolution model. Some locations have more than one coefficient. How to determine
Yeah.
which coefficient
So
contributes more
I've
to
gotten
those locations?
so that's another rephrase Yuan's question. So if we look at these nodes for our basis functions, we see that some of them are overlapping, that the same node. You know, that doesn't keep me up at night, and here's why. Is basically my particular perspective on this is that the processes that have different levels of resolution. Each of these processes should be well behaved. I should be able to formulate these in a way where they look like stationary processes. And I'm going to prescribe that they're independent, and I'm just going to add them up. Whether the lattice points line up or not, if these are all reasonable processes, when I add them up, I'll be essentially be adding up their covariance functions. Mischief, but not in this one. And I can't imagine the R coding I would have to do if I had to avoid lattice points at different levels. It's hard enough just keeping track of them the way they are. Okay.
Great, thank you. Any other questions? Are we good? NC State says it's writing. Why not wavelets?
Good.
Why
So
not
someone at NC State is really cooking there. Okay. So what is special about wavelets? So I'm using essentially basis functions that are bumps. Let me find one of these guys. So here's my little bump. If these were wavelets, when I translate the bumps, they would have orthogonality properties. Wavelets are compactly supported, just like these bumps. The reason I don't want to use wavelets is that they don't really buy me a lot more. The orthogonality really only happens when you're looking at equally spaced locations, and I am not doing that now. So when you're computing X transpose X, that you wouldn't get any benefits from wavelets there. So you wouldn't end up getting a diagonal matrix. The other thing that's interesting, as the candidate basis functions. And it turns out you have to work very hard to build standard covariance functions from wavelet bases. Now, maybe I'm missing something, but it was just very, very difficult and frustrating. I would get covariances that had a lot of the artifacts of the tensor product structure of wavelets in them. And as I said, with the irregularly spaced data, you weren't getting the orthogonality properties. So eventually, I decided just to go with something simple. Yeah, so that's about it.
Great. Okay, well, let's all thank
Yeah, and I'll say
Doug.
you're welcome,
Let me just do a
Chicago. I
quick
see.
add
Thanks,
her.
Doug. Okay, okay.
And I'll give you a clap for everyone. So thanks a lot. And our next online seminar will be Tuesday, 9th of December at 11 a.m. Eastern, and Monty Fuentes is talking about spatial statistics for
All right.
environmental health data.
You're
So
welcome.
thanks
Thanks.